So good morning, good afternoon, good evening, everybody. Welcome to the first of two sessions on control system upgrades. We have three talks for this session. There are opportunities for asking questions. You can ask live audio by putting your hand up at the end. You can also post questions to the Hoover Q&A or to the Zoom Q&A, but please, it's preferred that you don't use the chat function for questions. Okay. So I'll welcome our first guest, our first talker. Our first talker is Karen White, from a control systems section head from Oak Ridge National Laboratory, and she's going to talk to us about modernizing the SNS control system. So over to you, Karen.
你们那边有个主席正在问，为啥那个什么有个人拿到链接，本来是后边的 speaker， 就是说。
Heyan, can you mute, please?
Yeah, I can hear you.
链接都是一个呀，这长时间的呀。
什么？是打上的吗？
I should start.
Should I start?
I think so. Yeah, we're 32 now.
All right. Good morning. I'm Karen White. Thank you for the introduction. I'm going to talk today about modernizing the SNS control system. So now my slide won't advance.
Yeah, you can go on.
Okay, very good. Sorry about that. Okay, so just a little bit of background. The Spallation neutron source is an accelerator-based neutron source in Oak Ridge, Tennessee. It's a DOE.
The sanction is the project states.
Excuse me. Can you please mute?
Heyan, can you mute, please?
Yeah.
Thank you. It's a DOE user facility for neutron scattering research built by a partnership of 6 DOE laboratories. Construction was complete in 2006 and the user program began the next year. We now operate 4,500 hours a year, and we have 20 instruments available for users. We have 2 upgrade projects in progress, the proton power upgrade to double the machine power, and the second target station builds a second target station with a new suite of instruments for users. At that point, we'll have 2 target stations and share the beam on a pulse-by-pulse basis between the 2. So building the control system, the partner labs who built subsystems for the SNS built those systems with controls and delivered them here to Oak Ridge. The controls group at SNS was responsible for global systems and for integrating all the subsystem controls that were delivered. So in order to do this, the project decided on some standards for the control system, including the EPICS framework and tools, Allen Bradley PLCs, and Motorola VME IOCs. EPICS has been used to integrate controls now based on a diverse set of hardware platforms, giving the operators a common view. This is a look at the architecture. It's a common 3-tiered architecture. On the top, we have what the operators see, alarms, displays, archive data, and things like that. We use CS Studio primarily here. The communication layer where we use channel access, and this is services we include in this layer as well, like detecting alarms and archiving data, and also IOCs that run just on Linux machines that don't require hardware connections. And then on the bottom, we have where you would detect, connect to all your field devices. And here we use a variety of hardware platforms, including Allen Bradley, VME, MicroTCA, and LabVIEW running on Windows was implemented by the Beam Diagnostics group here for instrumentation. This is just the size of the control system in terms of nodes on our network. We started out with 168 VME IOCs, and we have about that many now, but they're not all the same. Some have gone away, new ones have been added. We, however, tripled the number of soft IOCs to support additional requests and new features in the control system. We're just in the last few years adding MicroTCA. So we have a few of those systems now. There will be many more in the coming years. The number of these LabVIEW IOCs for Beam Diagnostics has grown quite a bit. PLCs have doubled, and the number of process variables, so the unit that we use in EPICS to pass data around, has increased by 50%. Over our 15-year history. This is an availability graph. You can see there were some growing pains in the beginning, but now we maintain availability right around 99.5%. So initially, you know, we start upgrading the machine just as soon as we built it, right? We had to address those performance issues in the early years, and we have always been expanding the system by adding controls for new devices when other subsystems add things. We have added new tools and support for additional hardware types. We have to address hardware and software obsolescence. And it becomes more challenging once the machine becomes operational because you can't have long downtimes to do a lot of work on the control system. You just kind of have to fit this in during little maintenance days or scheduled machine outages. And our upgrades are always based on resource availability. How many people do we have that are available to work on these things? And how much money do we have for hardware? So I'll just go over what we have done in terms of upgrades over the life of the facility and what's going on, what we plan for the future. So in terms of infrastructure, we have, a network with 1,000 or so nodes on it. And of course, we have servers and workstations and all sorts of computers. And this type of infrastructure goes under constant technology refresh. We try to get in there and replace 15 or 20% of the network switches and things like that every year, so we don't end up where we have to replace them all in 1 year because the budget really doesn't facilitate peaks like that. And this way we are constantly refreshing that hardware. We're in the process of upgrading our Linux to 64-bit Linux. We had a lot of 32-bit machines in the system, and that's really something you can't get anymore. And this has been a long process because of all of the testing involved to be sure that everything you recompile works on the new operating system. For the future, we look at the network and its performance and think that we will have to introduce a more segmented network at some point because while things work well, we can see that there's more stress on the network. Sometimes names require multiple broadcasts to resolve and things like that. And with the control system set to grow for PPU and for STS, we know that we need to have a more well laid out network. Timing system was one of the first systems to show some obsolescence issues. And we developed this as an upgrade several years ago. We had new timing distribution hardware and a new timing master along with new software. That project was commissioned and completed in 2019. And machine protection system, we have installed new field nodes based on micro TCA. We have a new master in place. But right now we're working on firmware and software to finish this up. We have testing going on where the nodes out in the field basically record data but don't shut the machine down. So this is meant to validate that the new system would shut down the same time that the old system would, so that we ensure a constant level of protection once we switch over to the new system. As far as EPICS goes and services and the tools, when we started building this place in the early 2000s, EPICS 3 is what was available. And so we have had minor upgrades, but we fundamentally have an EPICS 3 based system. Now that EPICS 7 is available, allowing us to mix and match EPICS 3 and EPICS 4 protocols and IOCs, we have started to introduce EPICS 4 IOCs into the system so we can run channel access and PV access together. So switching to EPICS 7 will give us the ability to support more advanced data types and to have higher speed data acquisition for some of the new smart devices in the future. CS Studio tools have been developed. We have very active CS Studio tool developer here at Oak Ridge. One of the early things we did was a new archive engine and a new alarm handler, and these were some of the initial CS Studio efforts. The alarm handler that we had when the machine was built was really inadequate. It was kind of patched together at the end. We didn't have a really good tool for that. And when I came here in 2007, I literally could not walk down the hallway without somebody stopping me and asking me what we would do about alarms. So that was one of the things that we took on early in operations. And we now have this alarm handler in place for many years now that is serving operations well. Tools, we're also based on CS Studio, the tools we run in the control room. Compared to the different tools that laid on top of EPICS that we started using in 2006, the CS Studio tools provide interoperability and a common look, feel, and behavior, which is very beneficial for the operator. So we have a new archive browser at that time, a new alarm display. There's a new display manager, which is in use on the SNS instruments at this point. We haven't migrated it to the main machine yet because we have like 6,000 display pages, something like that, that need to be tested. You can convert them, but if they have embedded scripts or something like that, it requires additional testing. So that work is in progress. And we also added web-based displays, which is useful for people who need to try to troubleshoot their systems from home. And of course, it's been extraordinarily useful here in the age of COVID, where we have so much working from home. Soft IOCs, these are Linux-based IOCs where you don't need to connect to hardware. We have obviously tripled the number of those in the system. And this is often used to create composite or calculated PVs. On the front end, we started out with 100 or so Allen Bradley PLCs. Now we have nearly 200. In 2009, by that point, we had had a few failures of these PLCs, which would be unusual for that kind of hardware. And we worked with the manufacturer, and they were able to discover manufacturing issues on these early boards and worked with us to get those upgraded. So the processors aren't as old as everything else, but we're now looking at converting this slow and obsolete control net and device net communications that are used in many of our PLC-based systems to use Ethernet communications. On the VME side, we used a lot of VME in the beginning for real-time systems. These modules are getting harder to get. We've experienced some obsolescence. So in the high performance world, new systems are built with micro TCA. Turns out some of our VME systems in the beginning don't really need high performance. And in the cases where we get obsolete modules there, these systems are converted to PLC-based systems. For example, we had VME motor controllers, and we don't really need that kind of performance. So those will be redone in PLCs when their time comes. For micro TCA, this is our new real-time platform. We first did the Ring low-level RF with this. Now we're in the process of doing the Linux low-level RF, which will be needed for PPU and STS. And we have, for example, kicker waveform monitoring and generation, and the new MPS and micro TCA. So concluding, the SNS control system has been, under upgrades ever since it was released. It's growing, it's evolving since original commissioning. We are particularly vulnerable to vendor technology cycles causing obsolescence. We know that's how they make their money. And, you don't have to upgrade every time they put an upgrade out. However, when you can't get patches anymore, that can be detrimental, for example, to cybersecurity. So you have to stay on top of that. The original control room tools were very basic and needed improvement early in operations. These have been replaced with CS Studio services and tools. And the nice thing about this architecture, this three-tiered architecture that we have with the EPICS framework, is that we don't need disruptive changes to upgrade. This lets us phase changes in on any layer without disturbing the other layers or even on an individual device. So thank you very much. I said upgrades are dependent on resources. We're looking for a few good engineers, and there's my email address if you're interested. Thank you.
Thank you, Karen. Thank you for an excellent talk and bang on time as well. So I think we can afford a couple of minutes for questions. Let me see, there's one.
Yeah, we have 1 minute for question.
Yeah, do you want to run this together?
Sure.
Yeah.
Karen, okay. So there is one from Anonymous. They say he's interested in the 32 to 64 conversion, particularly for C++. What has been approach for modifying a significant code base? Any recommendations? Do you have any answers?
Yeah, we haven't had to really modify a lot of code so much as you have to recompile code and you have to test it. So, for the most part, we've been able to just recompile things. But, if you want to talk in more detail, just send me an email and I can put you in touch with the folks who've been working on that.
Yeah. Okay. The second one is from Furukawa-san. He said he has been increasing number of the NetView IOCs on Windows in PXI. Do you install any specific protection mechanism against the risk of the virus on Windows?
Yeah. Obviously this is an issue. So for the older Windows machines, we patch them as long as Microsoft releases patches, but they are behind a couple of significant firewalls. The control system itself is behind a firewall. We can cut all ties with ORNL in the outside world at that firewall and run independently. So we try to make it hard on the outside because we know there's really not adequate protection for older Windows machines. And the Beam Instrumentation Group, who does all these diagnostics, is moving away from Windows. They've actually replaced quite a few of these with the newer LabVIEW type hardware that doesn't run on Windows anymore. And so the long-term strategy would be to get that out of the system. It's hard though, it takes a lot of time, it's expensive.
Yeah, I think I fully agree. Okay, so we are 1 minute late. Maybe we should start the next one, Austin.
Yep, okay. Well, thank you very much once again, Karen. And
Thank you for listening.
Thank you.
Have a great day.
Thank you. Okay, our next presentation is by Vinod Gopalan, and he's group leader from Lawrence Livermore National Laboratory, and he's going to talk to us about modernising digital video systems at the National Ignition Facility, success stories, open challenges and future directions. So if you'd like to share, Vinod.
Yeah, can you see my screen? Okay,
I can see it and I can hear you. Great, off you go.
excellent. All right, hello everyone. Hope you are all doing well. So I'm Vinod and I'm a control system software engineer at the National Ignition Facility located in Lawrence Livermore National Laboratory. So today I'll be talking about our modernization efforts specific to a subsection of the NIF. This is with respect to the digital video systems in NIF. So here are the main topics that we'll be discussing throughout this presentation. So we'll start with understanding what exactly a digital video system is, and then talk about the challenges we had, and then briefly touch upon some strategies that we considered, present our solution, and take a peek at the future directions. So primarily, we'll be focusing on answering the question, how do we solve the long-term maintenance challenges of the digital video systems? First, let's start with understanding what digital video system is at NIF. So DVIDs provide critical diagnostics to study the laser and allow operators to observe the state of the system in real time. So the camera attached to these DVIDs may be used for still captures, could be used for streaming video, or it could be used for both. So with over 500 DVIDs deployed along the laser path leading to the target, the DVIDs provide machine vision functions to NIF, and this includes optics inspection, application-oriented machine vision processing, vision-guided, automatic alignments and positioning. So in summary, this makes DVIDs an integral part of the NIF control system. So while DVIDs play a big role, they also have significant maintenance challenges. So the first challenge that we had is that the 500 plus DVIDs run on outdated Windows XP operating system, and they are deployed as 500 separate images installed on 500 plus hard disk drives. So the diagram shows a simplified view of the DVIDs, each of which consists of an front-end processor, or FEP that we call it, attached to a camera, typically over a FireWire or a gigabit Ethernet interface. So the FEPs in turn are connected to an Ethernet network to communicate with other framework services and applications. So so it is clear that the OS has to be replaced with a more modern version. But at the same time, along with that, we also need a solution for the large number of individual images and the unreliable hard disk drives, that is essentially in each of these DVIDs. So the second challenge we had is the outdated DVID, the computer hardware itself. As the pie chart shows, nearly 2/3 of them actually need some sort of upgrade or need to be replaced so that it can actually run a later or modern operating system. So to support a modern OS, it was essential that we replace or upgrade the older systems. And the final challenge is the variety of software libraries and drivers associated with different camera interfaces, manufacturers, and camera, and camera types. So in the table, I've listed the different camera types that we use at NIF, more from the point of view of what kind of interfaces they use, and the different manufacturers from which we source these cameras. So each of these camera types typically comes with associated Windows driver software and often have proprietary licensing schemes that are different across different manufacturers or camera software vendor. So although we will always need a different camera types, depending on the application, for example, for different image resolutions, streaming rates, or various special features like radiation vibration tolerance, we will definitely need different cameras. But we still need a way to consolidate the software that controls these camera types. So that's the challenge we had. So so now that we have laid out the challenges, I'll present some potential strategies that we considered. So the continuous run of experiments in NIF means that an extended downtime of upgrades is not an acceptable option. So the DVID upgrades, as we planned, will use the proven in-place incremental upgrade in parallel with scientific operations, which is an approach that the facility has tolerated well as part of prior, NIF modernizations. So basically, the overall strategy follows the best practices of similar upgrades. Regarding the OS upgrade, we considered different options, including upgrading Windows to a recent version, as well as various Linux-based solutions. However, we wanted a solution that would also solve the multiple OS image problems as well. For camera software, we looked at various options available from the manufacturer, as well as other commercial software and open source alternatives. So here our goal was to design a generic solution that would work for all different camera interface types and camera types. So which meant we probably had to move away from manufacturer provided drivers, but that would create an additional challenge for us because manufacturer software usually provides additional camera maintenance tools and other software. So we'll have to find a replacement for that, or write tools of our own. So basically, we looked at various upgrade strategies here, studied the pros and cons, and came up with a solution that addresses the unique requirements of the DVIDs, which we'll talk about next. All right, so the first part of the solution is an operating system and bootstrap architecture that essentially solves the OS problem. So the diagram shows our new architecture. So basically, we created a Gen 2 Linux-based OS image that will be booted over the network by the DVID systems. And this Gen 2 Linux solution is not completely new. We have been running this solution for our VME-based FETs. So this was essentially an enhancement to an existing solution with specific additions for supporting the DVID features. Since the image will be network booted, the DVIDs can now be diskless. And the netboot system is built with 3 key technologies, the PXE or PXE, DHCP, and TFTP. And essentially, the PXE server serves the same single image that's to all the DVIDs, and that's a key part of the solution. This will make OS image upgrades and patching much easier because there's only one image to deploy, and the DVIDs will pick up the latest images automatically when rebooted. So this combination of single Linux OS image, network boot, and diskless DVID nodes essentially solves our obsolete OS, the multiple image challenge, and the hard disk drive maintenance issues. As for the last issue of supporting multiple camera types, we came up with the DVID software stack based on open source camera drivers. For our implementation, after extensive evaluation, we chose libdc 1394, which is actually a FireWire library, and another library called Aravis for GD cameras. So our solution is built on top of these 2 open source drivers. And for our software implementation above the driver library layer, we have a very generic implementation, which is based on YAML-based test text description files. So, so this generic implementation allows us to quickly add support for new FireWire Gigi cameras with minimal software changes. Performance testing is another key thing, so which involves analysis and optimization to ensure that the upgraded DVIDs meet or exceed, the performance of the systems that they are replacing. One example is, we use the Intel's IPP libraries to support or to perform fast image compression and decimation. So we had to kind of rebuild and test this on the Linux platform, and also have to optimize network performance by tweaking, for example, packet buffer sizes. So yeah, so in summary, by using a generic FEP implementation based on open source camera drivers, we achieved a clean and performant solution that's also very maintainable. With the implementation in place, the next step was to verify and deploy to the NIF production system. So to ensure successful production deployment, we have offline test environments to verify and do dry runs and deployments. And these offline environments have replicas of production DVID systems. And the production deployments itself involves multiple teams, software, hardware, scientists, and other stakeholders. So detailed procedures were written and followed to ensure coordinated deployment. That the deployments were done in place in a short time window so that we can ensure that NIF can continue to function in the event that deployment fails. We also had reward strategies in place to handle any failures. So yeah, as of now, we have the solution deployed successfully, and it's being actively used in NIF's 24/7 operations. Now with the long-term maintenance challenges solved, here are a few future enhancements that we are planning. So we are working on integrating the Gen 2 operating system into our continuous integration pipelines and planning for more frequent release cycles. We already did some efficiency improvements by combining cameras into the same DVID, and we are looking at increasing that number in each DVID further. So we also plan to enhance our homegrown camera maintenance tools by adding more features to it. With that, I'd like to conclude my presentation and open the floor for questions. Thank you.
Thank you, Vinod. That was an excellent talk. Camera isn't a big problem you've been solving by the looks of it. Trevor, are you going to do the Q&A?
Yeah, we did not. There's no question on the QA panel. Is there any live question to speaker?
So, I would be interested in knowing how long this took from start to finish, and do you feel like as soon as you've finished, you'll need to start again?
About 2 years is what it took for that. And so is your question that once we get complete this, or would we have another maintenance challenge by which we have to repeat this? Yeah. I think the solution is, pretty long term, and we won't need to redo the whole thing. We might still have to do patches and upgrades to the solution, right? For instance, for the operating system, we'll have to apply patches and upgrades. And for the software, we'll have to add support for, let's say, new camera types. So the architecture supports, those enhancements. And we think we can keep this overall architecture for the next maybe up to 10 years.
Okay, thank you. Thank you very much. Okay, if there's no further questions, should we move to our next speaker? If you could unshare,
Sure.
Thank you. And Thomas, if you'd like to share and get that going, make sure we can hear you. So to introduce our next speaker, we've got Thomas Jurgens, who was formerly from the Netherlands Institute for Radio Astronomy, Astron, is that correct? And is now,
that's absolutely correct.
And is now a controls software engineer at the Square Kilometry Array Observatory at Jodrell Bank. And
yes.
And Thomas will give us a talk on MOAR 2.0 station control upgrade. Thank you.
Thanks, Austin. Good morning, good afternoon, good evening, everybody. Thanks for tuning in. I'd like to give a quick update about the LOFA telescope's station control software upgrade, which comes together with the hardware upgrade. As Austin said previously, I've worked for Astron until last month, so forgive me that you see in the bottom right corner an SKO mentioning it's my new employer, so I owe them the time. All right, I'm joined by two colleagues from Astron, Jan-David Mohl and Thijs Schneider. Jan-David Mohl is the software architect. Thijs Schneider is a software engineer. All right, what is LOFA? LOFA is actually a telescope. It's not an accelerator. I'm very impressed by the machines you have presented so far. It's a radio telescope. It operates in the 10 to 270 megahertz regime. It's actually a distributed telescopes. Imagine that it is a telescope that has its dishes in several locations on the European continent, as well as in the UK or in Latvia. So we can create baselines with up to 3,000 kilometer baseline length, which improves significantly the resolution of a telescope. And we have also central processing unit that correlates the data once it's received by our antennas. Well, and a rough number of data that our telescope produces is around about 20 petabytes so far. We store the data in 3 locations, in the Netherlands, in Germany, and in Poland, in long-term archives where the data can be requested by our users. So, well, all right, it's a telescope, it's a radio telescope. And how does it look like? Well, it's unfortunately not impressive, I have to say. What you see in the top left here is a low band antenna. What you see on the top right, at the top right, is a high band antenna. So we have 2 different antenna types. The low band antenna is for the 10 to 90 megahertz band responsible, and the high band antennas are responsible for the 120 to 240 megahertz regime responsible. So the low band antennas, as you can see in the central picture, are set up in a pseudo-random patch, and the high band antennas are set up, as you can see on the right side in the central picture, in a more concentrated and condensed way of alignment. So in the bottom right corner, you can see the super tab. That's LOFA's core, where we have the highest density of antennas and dipoles, and that is located in the Netherlands. All right, so it's a telescope, it's 10 years old. It has shown its age, and now it's time to upgrade it. So what is the purpose? Well, we wanted to make it more powerful, which meant, first and foremost, we had to upgrade the hardware. Well, unfortunately, upgrading hardware, as my 2 speakers already clearly said, always means new software as well. Is it just an operating system upgrade, or is it even an upgrade that's for the control software, or for the monitoring software, or for the GUIs, or somewhere always when new hardware is introduced, you need new software. So that gave us the chance to get a new baseline for hardware protocols. So we agreed on OPC UA being the hardware protocol interface with the software, and Tango Controls was chosen as the new monitoring and control system framework. So we decided to not upgrade all stations at the same time, but station by station, but the Dutch stations first. What will they be capable of performing? Well, for the first time, the Dutch stations will be able to observe in the high band and the low band simultaneously, which allows us actually to apply proper corrections, ionospheric corrections, which disturb an image fidelity that is produced quite significantly. So we also introduced a new precision clock system that is based on White Rabbit and distributed all over the Netherlands. And that also increases the possibility to correct for distortions in the sky. The deployment is were aimed at 2022, 2023 in the Netherlands. There's another aim that we deliver a station in 2023 to ENAF in Italy. Well, how does a station look like? That is the aforementioned, if you want to call it a dish. So we have a cabinet, you can see here on the left. We have digital processing boards, also in the cabinet. We have filters and ADCs, also in the cabinet. Then we have our very important antennas. There will be the timing distribution that you can see at the bottom, White Rabbit receivers, central clock feeding the White Rabbit receivers. All the data will, with the help of monitor and control, be sent to a central processing cluster in Groningen. And everything at the station will be monitored and controlled through our telescope manager. Well, what did we have before? What are we going to have soon? Or we have already. Before, LOFA 1 ran on a custom controls and monitoring system with a bit of WinCC08. The software interfaces were all custom. There was no real baseline design. There were no streamlined interfaces. The hardware interfaces were really awkward to use from a software engineer's perspective because they were based on raw Ethernet. Software, most of the software was written in C++98. Only over the last 5 years, we have replaced some of the software with Python 3 software. But overall, LOFA 1 is a very expensive to maintain telescope when it comes to software. And so the decision was made to cut costs. All right, let's just get a good architecture in. Let's get a good software system in that has a hierarchy, that is maintainable, modular, and modern. So we base Tango controls. We base LOFA 2 on Tango controls, OPC UA, and plain TCP/IP where necessary. And where possible, we use Python 3. If it's unavoidable, we haven't seen a case so far, but where it's unavoidable, we would allow for C++ 11. Well, the result would be an easier to operate telescope, we hope. Definitely easier to maintain, easier to debug since it's all unified, easier to integrate because everything is Tango controls, OPC UA, and Python 3. And much easier to extend. My colleagues before me have already mentioned that it's hard to find capable software engineers. So by using just a small set of diverse things like Tango controls, OPC UA, and Python 3, we hope that we can attract more software engineers to develop software for our telescope. So all together, this should lower the operational costs, and enable Astron and LOFA to have improvements put much quicker into the production system than in the past. I show you here a quick model of our software architecture. So it's a hierarchical system that Tango controls strongly encourages. So what you see here is the yellow boxes are pure software devices. If you see in the top right corner, this weird icon, that's the icon of Tango controls. So you can see that most of the system is based on Tango controls. And where you see green boxes, this is from a software perspective view, hardware in the widest sense. So it's the cabinet with its fans and temperature sensors, the timing distribution, receiver subsystems. These are our antennas and dipoles and receiver boards, and the digital processor, which is the FPGAs and 32 FPGAs per station that also need to be controlled, monitored, and made happy and kept happy. So on the top left corner, you see we also have a monitoring cache. That is what we call it, a monitoring cache. That's actually a database, an archive for monitor values at the station level, and that is shared with a centrally hosted archive as well, so that we always at all times have monitor data at our fingertips and can essentially enable the operators to roll back in time and view what was the state of the system. We hope that we can provide enough monitor data that the operator can even say what the exact state at that time was. Well, I have mentioned tango controls already. As you can imagine, we are really grateful that tango controls exists. It's an open source project. It's free of charge. The community is extremely helpful. So we believe that tango controls is the monitor and control framework for the 21st century. It's allowing you to model a hardware in software in an object-oriented way. You can easily, through the enforcement of hierarchies, model your dependencies within hardware. It supports natively Python 3, which is just the language of choice nowadays in the scientific community. SKO has gone through the motions and provides Docker images already that can be just downloaded. You tweak them to your liking, and it's just fantastic. Within 6 months, we had the first devices running, talking to our hardware. So yeah, I can't really emphasize enough how great tango controls was for the success that LOFA 2.0 station control upgrade is so far. I show you here, we use Jupyter notebooks that give the hardware engineers very easy access to the devices, either software-only devices or real hardware devices, where the hardware engineer doesn't really have to care if it's a software hardware device. Why? Because the devices provide functionality. So it's a really software object-oriented design. Well, we have also upgraded to Grafana user interfaces. Well, actually, Grafana is more passive way of displaying things. It's just for monitoring. Control with Grafana is quite tough, so we're avoiding that. But Grafana gives you really good looking and easy to set up GUIs, and it was almost a no-brainer after half a day of just fiddling around of my colleague Jan David Mohl that Grafana is the go-to UI for monitoring.
Thomas, we have about a minute left for questions. So
yes,
like
I'm almost.
Yeah. Okay.
I'm almost done. As you can see here, I was talking about Tango devices. Like in EPICS, you have values that need to be fetched from your hardware. Actually, in Tango controls, we wrote a small helper wrapper that allows you just with one line of source code to access from an OPC UA server data values, read write or read only, have them automatically archived and. So, all right, what you can see here is, yes, we're using Jupyter notebooks. That was quite easy to integrate. We can already archive Tango controls attributes because it's also made very simple. We have Grafana running. The hardware engineers are already very happy with the Jupyter notebooks and how they can see what their hardware is doing. They're not forced to, lab view interfaces that simply don't scale. And everybody agrees in the program that choosing OPC-UA for station control and for hardware interfacing, it was the right choice because it made it even very simple to have OPC-UA servers running in simulation mode so that the software engineers don't have to have hardware at their fingertips when they want to integrate something. Thanks to our colleagues from ENAF, they provided 1 FTE for software development. They did front-end RCU2 development, and thank you very much to SKO for the Docker images and for the expertise and advice. Thanks for listening. Thank you for your time. And Astron is looking for Tango controls programmers. Please help the good cause. If there's still time left, please ask me any questions you like. Thank you very much.
I think we'll have to put the questions on hold and perhaps people can contact Thomas directly because
All
we
right.
need to hand over
Yes.
to the next session now. We are a minute late handing over. So over to the next session. Thank you very much, everybody.